Hello everybody, and welcome to the beginning of section 1.6. We're looking at page 29 of the workbook here. And in this section, we're going to be talking about bases and dimension. These are two huge definitions in linear algebra. We're going to see that they unify a lot of the concepts that we've been talking about up to this point in the course. And I think the best way to get the ball rolling here is just with an example. Okay, so let's read this example together. So they give us 6 vectors, v1 through v6 and r4, and we're going to be discussing a subspace that looks like this. W is the span of these 6 vectors. We know from our previous work that W is a subspace. And here's what they'd like us to do. We'd like to find a linearly independent subset of S that spans W. Okay, so kind of the thinking here is, or the implication in this statement is that maybe we don't need all 6 of these vectors to span S. Maybe we can throw some of them away. Okay, the implication here is that they're not linearly independent, which means that there are some dependencies among these 6 vectors. Okay, so that's kind of where we're going here. All right, so let's start with an observation. So because W is the span of these 6 vectors, if we start with kind of an arbitrary vector in W, then we know that we can build it as a linear combination of those 6 vectors. Okay, in other words, there will exist scalars such that this equation is satisfied. Okay, C3V3. Okay, this is a little bit of writing here. Is equal to W. And we know from our previous work that an equation like this can be rewritten in the form of a system. That's what we're seeing down here on this line. Notice that the columns of this matrix are just the 6 vectors that they gave us. Okay, and the right-hand side is the vector that we call W. Okay, so if we wanted to solve this system, we would do row reduction. Okay, and I went to Mathematica and did the row reduction and came up with this matrix over here. Okay, notice that the right-hand side W, the A, B, C, and D that we started with, those numbers are going to change each time we do a row operation. So I'm just calling the first 3 A prime, B prime, and C prime. Okay, not really important what those are, but something interesting happens in the last row. We end up getting a 0 there after we do our row operations. Okay, now what I'd like to do is to see if we can spot our pivot positions. Okay, and remember a pivot position, we're looking for the first non-zero entry in each row. Okay, so in the first row, we've got one there. In the second row, there's the first non-zero entry, and then the third row there. So we've got 3 pivot positions. And here's the claim that we're going to make. Okay, remember back to the original problem, we're trying to find a linearly independent subset of the 6 vectors that we started with that still spans W. Okay, I claim that we can do that by just looking at the pivot columns. Okay, so taking the vectors that correspond to our pivot columns, that would mean taking V1, V2, and then V5. Okay, let's write that down. V1, V2, and V5 is the desired set. Okay, well, how do we prove that? Okay, well, let's first remember what we're saying. By saying that this is the desired set, we are saying that beta has 2 properties, that it's linearly independent and that it still spans this subspace V or subspace W that we're talking about. Okay, so here comes the proof. What we're going to do first is imagine taking the big matrix that we started with and delete columns 3, 4, and 6. Those are the columns that don't have pivot positions. Okay, let's write that down. Okay, and we'll give that a name. Those are really the free variable columns. Okay, and just so we can picture this a little bit better, I'm going to actually do that. Okay, so let's clear a little clutter away here. Okay, and I'm going to actually strike out those columns that we just got rid of. Okay, and we'll do it here as well. Okay, so just imagine that those are gone. Okay, well, if we do that, then this system still has a solution. Okay, even if we get rid of those 3 columns, it still has a solution. Okay, this is still a consistent system. We would discover that whatever vector we put over here for W, we can still find a solution to this reduced system. So that's our first comment. So the span of beta is still W. That's one of the 2 properties that we wanted to have. And what about linear independence? Okay, well, after we got rid of those 3 columns, okay, that we just crossed out, notice that there's a pivot in every column of the remaining matrix. Okay, since there are only 3 columns left, that tells us then that those 3 remaining vectors that correspond to the columns that we kept are linearly independent. Okay, so let's add that to our explanation here. Beta is linearly independent. Okay, because after deleting the said columns, there are no free variables remaining. We got rid of them. Okay, and if you look at that, we proved that exactly what we wanted, namely that this set beta that we have here has both of the properties. It spans our subspace W and it's linearly independent. Okay, and this brings us then to one of the biggest definitions in linear algebra. Okay, there's a special name for a set that has both of those properties, that's linearly independent and that spans a subspace at the same time. It's called a basis for a vector space. Okay, so let's read the definition together. A basis beta for a vector space V is a linearly independent subset of V that spans V. Again, it's got to have those two properties together. Okay, so our first example of a basis is the set that we just came up with above. Okay, so beta equals V1, V2, and V5 is a basis for W in example 1. Okay, and before we go on here, just want to say one more word. We're going to do a lot of work with bases in this section, but these 2 properties that we have are absolutely fundamental, and I'd like to think about them one at a time. So linear independence. Okay, so a set being linearly independent conceptually is about the set being small enough so that there are no dependencies among the vectors. Okay, in contrast, a set of vectors spanning a vector space, that's about the set being big enough. It's got enough vectors in it so that we can build every vector in our vector space. Okay, so being a basis is like being big enough and small enough at the same time to have those 2 properties. So in some sense, the number of vectors in a basis is just right to get both of those properties at once. Okay. And finally, let's conclude this video just by talking about a general principle. This just summarizes what we did in the example at the top of the page. So read through this together. Let V be a vector space with a subset, U1 through UN of our vector space, and we'll define W to be the subspace spanned by those vectors. Okay, given some vector W and W, that means that there will exist scalars so that we can build that vector W that we chose as a linear combination of the vectors in our set. Notice that this setup is exactly the same as the setup in example 1. Okay, and so the conclusion is going to be the same as well. If we want a basis for W, we can obtain it by deleting all vectors in the set that correspond to scalars in star up here that are free variables. That's exactly what we did up in example 1. Okay, and this is a technique that we're going to use often in this section to find a basis for a vector space.